Welcome to this video providing a high-level overview regarding Kaloom's jointly developed solution with RedHat, a solution which solidifies the Kaloom Cloud Edge fabric for emerging 5G edge data centers and based on open networking principles with RedHat OpenShift as the foundation of a unified edge solution for network, compute, and storage. In the realm of 5G, numerous applications are emerging, namely virtual and augmented reality, industrial robotics and controls, also known as the Industrial Internet of Things, as well as interactive gaming and remote medicine, to name a few. These applications require a latency, cost point, service availability, and capability to work at a scale that simply cannot be delivered via the use of virtual machines running in a typical public cloud infrastructure. Many of these new applications require an end-to-end latency below 10 milliseconds. Unfortunately, typical public clouds are unable to fulfill such requirements. For example, the latency from New York towards Amazon Web Services or Microsoft Azure in Northern Virginia is greater than 20 milliseconds. When considering how these emerging applications in the era of 5G are best packaged, as virtual machines or containers, the answer is quite clear, pointing to containers as the way to go, with several key reasons. For example, in the event of failure for a given virtual machine or machines, several virtual network functions demonstrate severe service unavailability. Often, it takes several minutes to restart a VM after a crash. Such system behavior is not acceptable in latency-sensitive applications. In addition, since containers don't package system resources as much as VMs, you can run at least twice as many applications on the same server with containers than if you were to run them with VMs. This advantage maximizes resource usage and brings down operating costs. As well, with agile development and testing, faster time to market is achieved with containers, more so than if VMs were to be used. Therefore, with these considerations, one can easily see how the overall cost effectiveness of deploying containers versus legacy VM-based applications becomes truly compelling. And yes, at the end of the day, it's all about total cost of ownership. Today, service providers are grappling with the challenges of making their networks more efficient as they aim to deliver higher throughput and avoid bottlenecks. To address this demand, they look to distribute their data centers at the edge to lower the latency and improve performance of their mission-critical applications. But there are many edges. For example, telco edge data centers have several constraints because they must fit with an existing legacy central office. As a result, they must contend with very limited space, power, and cooling as part of their infrastructure. These telco edge data centers will need to host a variety of container-based applications, namely real-time interactive applications, content delivery networks, basic networking services, mobile and fixed packet core nodes, as well as IoT frameworks. To pull this off successfully, an infrastructure comprising compute, storage, and networking is required. Those container-based applications can be hosted in a 20 RU edge data center infrastructure comprised of compute, storage, and networking nodes. For a typical edge data center configuration running a Kubernetes application container platform, the configuration would most likely comprise the following: a gigabit Ethernet management switch, 3 servers to support the fabric and network overlay controllers, 2 network fabric switches, 3 servers for Kubernetes masters, a minimum of 3 servers for 5G UPF for mobile access termination and to manage half a terabit of mobile traffic. This would leave space for only 8 application servers to be made available for customer Kubernetes worker nodes. These 8 servers may not be sufficient to run all the required applications and would leave less room for monetization. When comparing a conventional edge data center having a Kubernetes container orchestration platform to that of an OpenShift-based joint Kaloom RedHat Unified Edge solution, the following observations are noted. In the Unified Edge configuration, the switches are Open Compute Project accepted white boxes, each equipped with a Xeon processor along with a high performance and fully programmable packet processor. The 3 Xeon CPUs on the 3 switches run the 3 OpenShift masters, the Kaloom Fabric Controller software, and the Kaloom UPF control plane as a container networking function. Moreover, in such a configuration, the 5G UPF data plane is executed on the Intel Tofino ASIC and FPGA devices within the 3 switches. Such a solution provides a 5G UPF with much higher throughput, lower latency, and an improved cost-performance ratio when compared to solutions based solely on traditional x86. Within the same 20 RU space and within the same power constraints, the Kaloom RedHat Unified Edge solution, having OpenShift running over switches, application and storage servers, provide 8 additional and potentially monetizable application servers as compared to existing container application platforms. These additional freed up servers run all the required applications within the given constraints and provide a lower cost due to the utilization of containers rather than VMs, and a lower latency resulting from the deployment of container applications at the edge. The Unified Edge solution enables the virtualization of the edge data center itself. For example, it is possible to create virtual data centers whereby one may have 10 physical servers and another one with 6 physical servers, depending on the application requirements. This is possible because Kaloom's Cloud Edge Fabric natively supports network slicing, whereby an edge data center can be partitioned into multiple independent virtual data centers, with each virtual data center being provided its own virtual fabric called a VFabric. Each virtual data center with associated VFabric can be assigned to a different virtual data center operator. In this regard, slicing permits multiple operators to share a common distributed cloud infrastructure, with each entity enjoying full isolation down to the hardware level for better security and a better quality of experience. The following provides a glimpse of the hardware involved in a typical small-scale unified edge solution, whereby the 3 Intel Tofino-based P4 programmable switches form the basis of the Cloud Edge fabric, and the OpenShift worker nodes shown below, which can host container applications. In the upcoming sequence, we are providing a demo which consists of a 5G standalone packet core deployed on Kaloom's Unified Edge. It shall be noted that OpenShift is running on compute, storage, and networking hardware. This demo begins with the OpenShift console showing the nodes and status of the 3 Fabric controllers and the 3 workers. In the Kaloom Fabric Manager view, the same nodes previously shown in the OpenShift console are observed with the associated links. Information regarding one of the Fabric controllers is displayed and its internal IP address will be used to show its switch port status. At this moment, we see Kaloom's Cloud Edge Fabric services running in the selected Fabric controller along with OpenShift cluster services. Now we observe the node details of a worker machine which can be used by a Cloud Edge user to deploy workloads using the OpenShift platform offered by the Cloud Edge Fabric. On this screen, one can observe 4 virtual fabrics which have been created by the DSIP for 4 different users who can individually connect to and manage their own VFabric via the management interface URL. Now we see a previously created VFabric existing in the OpenShift cluster which can be accessed via the OpenShift console and observe its details. Displayed here is the storage created for the demo to support the persistent data for the fabric. Now in this final sequence of events, one can observe dashboards containing various metrics for the projects within the Cloud Edge platform, which may be composed of Fabric, OpenShift, or end-user processes. In summary, Kaloom and RedHat have extended their collaboration to provide a jointly developed unified solution for distributed edge computing that allows network, compute, and storage nodes to share the same underlying container-based execution environment. Integrating Kaloom's Cloud Edge fabric with RedHat OpenShift will enable the platform to help simplify complex next-generation networks and accelerate time to market of new services while reducing the cost of edge infrastructure. For more information, please visit www.kaloom.com.